So in this video we are going to have a look at the questions you need for quiz 10. It's a revision quiz on CC1 and CC2, which you would have done way back in year 9. So really important that you take the time to revise this, because it's not difficult if you've just gone over the content. First questions are about chromatography. You're asked to calculate the RF value. To calculate the RF value, you need the distance moved by the spot divided by the distance moved by the solvent. And you can see on your little picture that you've got lots of spots, but it says here they want the dye that is present in both inks X and Z. So if I go to X and I go to Z, you can see they both produce 2 spots, but there's only one spot that's at exactly the same height. So that's the spot that's present in both X and Z. So I want the distance moved by the spot. They give you a ruler, so you don't need to use your own, but you need to be able to read the ruler they've given you. And if you look at it nice and closely, they say that the distance moved by those spots is 3.9 centimeters. Then we want to divide it by the distance moved by the solvent. See here, this is the solvent front, and the solvent front has moved 6.5. So you do 3.9 divided by 6.5. So you get 1 mark for writing that down. And if you actually do the division and give your answer as a decimal, 0.6, you get actually they'll award either. So you can give your answer as either. It's just for 1 mark. The next one, what could you do to make the RF value more accurate? This is a question that was really poorly answered the year this came up. To make this more accurate, you actually want a longer bit of paper, because if you've got a longer bit of paper, you get better separation of the different dyes, and therefore you're going to get more accurate RF values. So that's a tricky one there. You need a longer piece of paper to get a more accurate RF value, and that's the only thing that it's acceptable. The next one, sample Y did not move from the start line. I changed the experiment that would be needed. So Y is here, and as you can see, it stays in the start line. The reason it stays in the start line is because it's not dissolving in the solvent. So let's just say you used water as a solvent. If Y doesn't dissolve in water, then Y is not going to move. And that's clearly what's happening here. It's stuck on the start line. So to get around that problem, you need to use a different solvent. So you could use ethanol, you could use hexane, you could use any other solvent and try and get Y to dissolve. Once it dissolves, it will separate. So you don't need to be able to suggest solvents, okay? You can say use a different solvent, and you have to explain why, so that Y will dissolve. Okay, it's 2 marks, 1 for saying use a different solvent, and a second so for suggesting that you need it to dissolve. Right, the next question, I have done the answer, but we'll just go through the graph before we look at the answer. So you're given a heating curve showing the state changes, and the first thing you're going to need to do is just figuring out what's occurring at each point in the graph. So you can see here you've got temperature. So temperature is increasing, and you're starting out here at A, and temperature increases, and then your substance melts. Before your substance melts, it must be a solid, because solids melt. You heat up a solid, then it will start to melt. So you can see here between B and C, that's when it's actually melting. And after a solid melts, it's going to become a liquid. So between C and D, it's going to be a liquid. And you're asked to explain the shape of the graph in terms of the changes in the movement. So you're looking at changes in movement and arrangement of particles as the substance is heated. So a lot of you will know this information, just talking about how particles can move and how they're arranged in a solid and a liquid. But the important part here is changes. As you are heating that solid, how are the particles starting to change? And specifically, you need to know what's happening here between B and C. And because they're asking about the shape of the graph, you're going to need to explain why that graph is flat. All right, so between A and B, we said it was a solid. Hopefully you know that in a solid, the particles are arranged in nice, neat rows. They're all touching each other, and in terms of movement, they can only vibrate around fixed positions. But as you're heating the solid, they will start to vibrate more and more and more, because ultimately they need to be able to pull away from each other, so they'll start to move more and more. So what I've written here is just for a solid. I've identified that between A and B it's a solid. I said the particles are arranged in a fixed position, they're in neat layers, just like what I've drawn here. I can say they can only vibrate, but they will start to vibrate more as the temperature increases. So I'm talking about the change as I'm going from A to B, they are starting to vibrate more. Then you've got between B and C when it's melting. So to melt, it has to go from a solid to a liquid. And if I just draw a liquid, you'll see that the layers are disrupted and the particles are still touching each other, but they are further apart than they were in the solid. And in order for them to move further apart, the bonds that are holding these particles together are going to need to break. And when you're melting a substance, you are still heating it. You'll notice here that the temperature of the substance doesn't increase when it's melting, because all of the energy you're putting in is going towards breaking those bonds and separating the particles instead of raising the temperature of the substance. So I've written here that the particles are using the energy to break the bonds and become randomly arranged, because they are randomly arranged in a liquid. Okay, there's no increase in temperature, so I'm explaining why the graph is flat. So you could say the graph is flat at this point. There's no increase in temperature as all the energy is being used to separate the particles instead of being used to raise the temperature of the substance. Okay, but essentially at this point here, those bonds are being broken, those particles are getting out of their neat layers and into liquid form. And then between C and D, it's going to be a liquid. The particles are touching, okay, they are still touching if you look at my diagram, okay, but they are randomly arranged. They're no longer in those neat layers. They can move freely, and then again, as the temperature increases, they can move faster and faster. So again, I'm talking about the change. As the temperature is increasing, they're moving faster. Now, my answer is slightly more detailed than what it needs to be for 4 marks. You have to mention this point here about what's happening when it's melting. You need to explain why the graph is flat, but then it said any 3 other points out of these 2, and you don't have to be quite as detailed, okay? But it is content that you know, but that you need to apply that content to this situation. The next question is about potable water. Okay, this also comes up in CC2. So potable just means drinkable. It says a sample of potable water contains impurities, and that's really key. Potable means drinkable, it doesn't mean pure. Tap water is drinkable, but it's still got stuff in it. It's got minerals in it, but as long as those minerals don't harm you, as long as they're not toxic, you can still drink that water. So your answer here is going to be C. The impurities that are in there are harmless, therefore the water is safe to drink. In order to get potable water, you need to go through sedimentation, filtration, and chlorination. So you need to know what these terms mean. First one, what is sedimentation? Sedimentation is just when you let particles settle to the bottom. So it's C. So you basically just let the water sink in sit in a tank, and then all of the kind of solid particles will eventually just settle to the bottom, and then you can get rid of them. Why is the wastewater filtered? If you filter something, you want to remove insoluble solids. You can suggest the name of a solid, so something like sand, but they won't accept anything bigger. Things that you might find in the river, like branches and twigs and plastic bags, or I don't know, the old shopping trolley, all of that is going to get removed before it gets to the filtering stage. So when they're filtering in the water reservoirs, you're only going to be removing small insoluble solids, something like sand, but nothing bigger than that. And then you're going to add chlorine, and the reason you add chlorine is to kill microorganisms. They'll also accept kill bacteria. It's to make the water safe to drink. We are drinking river water, so obviously you wouldn't want to drink that without it being properly purified. The next question, you've got 2 liquids, they're mixed together. They want you to suggest how you're going to separate them. And they've given you the boiling points of the liquid, and this is key to describe how you're going to separate them. Because they've got different boiling points, you can use a process called distillation. Now you can use simple or fractional, they don't mind, okay, but you're saying distillation. And what you're going to do in distillation is you're going to heat both liquids, and because nickel tetracarbonyl has a lower boiling point, your nickel tetracarbonyl will evaporate first. So as soon as you heat the mixture to 43 degrees, this one here is going to evaporate off, will evaporate. You can then cool and condense it back into liquid form. And the other liquid that you've got here, iron pentacarbonyl, that's just going to stay liquid. As long as you don't heat it as far as 130 degrees, that one will stay liquid, while that one becomes a vapor, and then you can cool it, condense it, and you've got 2 separate liquids. So 1 mark for distillation, 1 mark for suggesting heat, and then a 2nd mark for suggesting what happens after you heat it. This one will evaporate. You could say why, because its boiling point, BP, is lower. That's why it evaporates first. The next one, again, you're using this kind of process of distillation. You've got seawater, which we know contains salt and water. You want to separate the salt from the water. If you heat, what's going to happen is the water will evaporate, the vapor will rise, it will enter this tube, it will cool, it will condense, and you can collect it as pure water. The salt is an ionic compound. It's got a really high melting point, and even when you're heating it, the salt will not evaporate. So explain how the water and seawater separates. So you're going to say you're going to heat and the water will evaporate. So it's going to evaporate first and then it will cool and condense. You could, I don't think it's on the mark scheme, but you could say the salt does not evaporate, and the reason would be its melting point is its boiling point in this case is too high. How could you improve this? I remember marking this before, and a lot of students were saying, you know, put a seal here and stop any water escaping. It is going to come out of this tube as a liquid, so it's not going to be able to escape out the sides as a gas. Also, if you were to seal this, you'd have a closed system that you're heating, and the pressure could build up and it could explode, so you're not going to be adding any sort of seal. Instead, what you're going to do is you want to make the cooling process more efficient. So if this tube is really cold, then it's going to be easier to condense the vapor. So what you want to put around this is you want to put a condenser. At the moment it's just a tube. What you want is to put a condenser around the tube, and the condenser will keep the tube really cold and make it easier to condense that water. So you're going to say add a condenser to cool, so you need those words, condenser and cool, to cool tube. And that's going to make the process of condensation more efficient. I've got one more page sometime. Was that the end of it? Was that the end of it? What was page? No, one more. Page 6. Just a multiple choice question. Which of the following will be solid at 20 degrees but will melt when placed in a beaker of hot water at 80? So I've got from 20 up until 80. And I want it to still be solid at 20 degrees, but I do want it to melt by 80. All right, so this one here is a melting point of 122, therefore it will still be a solid at 20, but it's not going to melt at 80, so that's not going to be the correct answer. This one will not be a solid at 20 degrees, it already becomes a liquid at -7, so that's not the right answer. This one will be a solid at 20 degrees, but at 30 degrees it's going to become a liquid, which means if you put it at 80 it will be liquid. This one here, -32, is already going to be a liquid before you hit 20 degrees, so the answer there is going to be C. So I'm just looking at the melting points. The boiling points here are irrelevant because you're only being asked about when it's going to melt. There's a carousel quiz as well, so make sure you do it to learn the knowledge. Don't underestimate this topic, okay? I know it's just states of matter, but as you can see, some of the exam questions require a bit of detail, so it's important that you practice doing them.